Good afternoon, everyone. So like yesterday, we have today Simona Binetti from Milano, Bicocca. Simona is here from last week as part of UNSW program of Women in Engineering, and she will be here until tomorrow. That's a bit sad. Simona did amazing. So she did undergrad in physics, master in material science, and then PhD in chemistry. So she covered all the range possible, and she's well known for her work on defects, mainly defects in silicon. So yesterday she covered the work that her group was doing on thin film, but today is mainly on the defects work, defect-related work. So she's associate professor in Milano Bicocca. She is vice director of the Solar Research Institute in Milano Bicocca. She's very active in the European range or European area of the silicon and solar cells research. Many grants and many projects that she is involved. And today she will try to cover part of that at least. So please welcome Simona. It's great to have you again.
Thank you. So thank you very much for this kind introduction. And so today I'm talking about photoluminescence and infrared spectroscopy for identification in defect in silicon for photovoltaic application. Sorry. I know that you are very familiar about the following facts related to photovoltaic energy, but I will start to this point because you know that now the cumulative PVC capacity installation exceed 550 gigawatt in the world, and according to different measure scenarios, we have we will have a very key role of photovoltaic energy in the next years. And this is very important because if, according to the best scenario, we will have in 2050 more than 4,600 gigawatt of installed PV capacity, this means that we will avoid at that time the emission of up to 4 gigatons of carbon dioxide annually. And we know that this is really very important. And of course, if we are wondering which technology is responsible of that, you know quite well the answer, and it's just a crystalline silicon solar cell. And it's important to say that thanks to the most important work that has been done by this research center in the last 30 years. Why? Because the silicon advantages are very well known. There is a good availability. Silicon is the second earth abundant material, of course, in the form of silicon dioxide. The silicon dioxide is no toxicity. It's a low cost because the price of photovoltaic solar energy has reached very low values. It has a very high efficiencies both in solar cell and then in modules, long lifetime, more than 40 years, sustainability, and also a very well established process has been defined for recycling end of life modules. So it seems that up to now silicon has no competitors. Sometime we take for granted the fact that this is based on the capability of purifying silicon at a very extreme grade. Silicon is the most perfect material that can be grown on the world, and but its quality but producing the right wafer is not the end of the story, because you know that there are a lot of processes involving a number of high temperature steps with the potential incorporation of contaminants, but also with the opportunity to rearrange them, because we know, for instance, that in silicon solar process, gathering or the p-n junction formation can cause a positive gathering of metal impurities, and also we know the benefit effect of hydrogen during silicon nitride passivation layer. What we are aiming for in a silicon PV, we know that the efficiency is the key driver, but to get efficiencies higher than 25% for monocrystalline silicon and 20% in multicrystalline silicon, it's important to have a better knowledge of the quality of our material. So the impurities, and also in the case of multicrystalline silicon, we have to work to reduce the impact of defects like dislocation, grain boundaries, and impurities related to Then, for the next generation, to make tandem solar cell with silicon, it's really very important, but we know that if you want to make a monolithic integration of another type of material on silicon, we have to control any contamination that can come during the process that can affect and can reduce the efficiencies of the silicon bottom cell. So dealing and controlling defect, it's still really a priority in silicon PV technologies, and to manage impurities and defect in silicon requires a deep optimization and knowledge of the process to produce silicon and cell as well, development of new analytical tools to detect the impurity quantity and to detect and quantify the impurities in level below the part per millions per atoms, and also correlate any process to defect and the subsequent defect iteration. I will try to show you during this presentation that by a simple photoluminescence or other simple technique like photoluminescence and infrared spectroscopy, it's possible to get a lot of information. You can see that by a comparison between two PL spectra, one collected on monocrystalline silicon, high purity, and the other collected on a solar grade multicrystalline silicon. You can see that there is a strong difference between them. Of course, it's still important, it's still a priority, but it's really an old story. If you do a very quick web search and you put just on Google silicon and impurities, you can find more than 8,000 works. And some of these works are very old and concerned with fundamental physics. I just reported this one because it's a rather bit older than me. And then we can find a lot of reported luminescence systems, but mainly I refer to irradiated, heat-treated and contaminated silicon or concern silicon for microelectronics. So the idea of this presentation and the outline of my presentation is, after a brief description of how photoluminescence and infrared techniques work as analytical tools, I will try to make a summary of the most important luminescence line and infrared peaks for a solar silicon. I mean, related to dopant, oxygen and carbon and dislocation. And then I will report some example of using photoluminescence infrared, and also then the quite strange a new approach to study impurities in silicon. So photoluminescence spectroscopy became very popular in the silicon field, thanks also to the work carried out by Trupke, co-worker in this center, because it's a very easy and fast technique to mapping the lifetime. It's a non-destructive method to map the lifetime and also the failure that you can have in a solar cell. But photoluminescence can be used also for detection of impurity level and detection information. Defect information. So how it works? If you heat the silicon with a laser excitation with energy higher than a band gap, you can create, of course, electron and hole pairs. And if you are at low temperature, they can form quasi-hydrogenic particles that are the free excitons. Then, at low temperature, the free exciton can recombine, emitting a free exciton luminescence that is phonon assisted and can be detected in between 12 Kelvin and 70 Kelvin, or at lower temperature the free exciton can be captured by shell of donors and acceptor and can give rise to impurity specific bound exciton luminescence, non-phonon or phonon assisted. If you have a level in the band gap due to the presence of some defect, you can have a radiative transition between band and impurity states. You can have, in this case, a deep transition or shallow transition. The deep transition can be seen also up to room temperature. The shallow transition can be seen usually at temperature lower than 12 Kelvin. If you have both donor and acceptor or level close to the respective bands, you can have a donor-acceptor transition. This is much more common in a compound semiconductor, for instance in Kesserite and CIGS, but it is still present also in silicon in some condition. And this can be visible between room temperature and liquid nitrogen temperature. Infrared spectroscopy is much more simple. It's very well-known technique. It's used to quantify the impurities in many materials, and in silicon mainly for oxygen and carbon, because it's a good sensitivity, it's very simple, it's non-destructive, and also the most important advantage is that the quantitative result can be obtained because the intensity is related to the number of bonds to the specific type absorbing infrared radiation, and so can be used to quantify the impurities. Probably you don't know that you can detect it by infrared spectroscopy also dopants, but in this case you don't detect the vibrational modes of dopants, but the electron transition from the ground state of the neutral impurities to a series of hydrogenic-like levels. At low temperature, it is possible to detect a series of lines related to this electronic transition of different types of dopants. So this is here is reported the boron cases, but from the strongest absorption band of different types of impurities, dopant, aluminium, antimony, arsenic, boron, gallium, indium, and phosphorus, a calibration factor has been calculated, and so it's possible to make a quantification of these impurities by infrared spectroscopy after low temperature. The problem is that usually you have to use thick samples, but if you use a thick sample, you can have a detection limit very, very low, of the order of 10 to 11. That is quite amazing, considering that you are performing just a simple infrared spectroscopy at a low temperature. It's possible to detect also the dopant determination in compensated silicon by infrared spectroscopy. Of course, in the case of compensated samples, you have to illuminate with white light in order to allow the neutralization of the dopants. But in the case of multicrystalline silicon, maybe many of multicrystalline silicon contains both donors and acceptor, in the case, for instance, of solar grade material, and you have some drawbacks relate to the fact that you have usually low thickness, so you can have a strain, or you can have also the simultaneous presence of dopants can cause a broadening of the peak, and this broadening increase with compensation ratio. So it's not always simple to detect dopants in compensated multicrystalline silicon, like in the case of monocrystalline one. But in this case, you can use photoluminescence. Photoluminescence is able to detect the dopant independently of the concentration by detecting the bound exciton lines related to different type of dopant. So each type of dopant can be seen by checking the bound exciton lines of the dopants. This, of course, must be done at very low temperature, at 4.2 Kelvin. But is the first work in which you can have quantitative information, very accurate, by photoluminescence. This work was done by Professor Tajima in Japan many years ago, in 1978, and there was a very good correlation between the intensity of the bound exciton line with the dopant concentration, and with a sensitivity lower than 10 to 10, and the upper limit is 10 to 15. So it means that in the case of multicrystalline silicon, or silicon for solar grade, or silicon, sorry, for photovoltaic, cannot be used. But recently, the same Japanese group, developed a new calibration in order to use this system also for multicrystalline or monocrystalline silicon. And it's possible to have a very accurate quantification of dopants in your material, and has been done a correlation with much more expensive, much more time-consuming technique like second ionized spectroscopy and ECP mass spectroscopy. In silicon, you can have also donor-acceptor pair. It's not so common, but you have a compensated material, but also level both close to the conduction band and level closer to valence band. You can detect the donor-acceptor transition. And in a quite recent work that we have carried out in collaboration with Tajima and also in collaboration with Daniel McDonald of NNU, University of Canberra, we studied the donor-acceptor transition in boron phosphorus compensated silicon. And we detected the band, and also we have seen that in solar gray silicon you can have this band, and this band increase increase with the compensation ratio, so can be used as a fingerprint of the compensation in your material, and also you can use this band to check the compensation ratio of this material. If you perform a much more different analysis of this band, just looking to the intensity and to the position, but we check the fine structure of this band, we can have some information about the dopant ionization energy, or if are not dopants, the ionization energy of this level closer to the respective bands, conduction or valence band. Because there is a relationship between the position and also the dopant ionization energy and the Coulomb interaction between dopants at low temperature. So by making this analysis, we succeed to define that no formation of boron and phosphorus complexes can be formed. No boron and phosphorus complexes can be formed in your material. And this was quite important at the time, because probably you remember that there was quite strong debates about the fact that in compensated material you have less light degradation effect, because there was a sort of competition between the formation of boron and oxygen and boron and phosphorus complexes. But by this work we have seen that if you have both boron and phosphorus, there is no any possibility on formation of boron and phosphorus complexes. Then let's move to the most common, the most famous light, called the light impurities, oxygen and carbon. Carbon, it's very well known that can be detected by infrared spectroscopy just by checking the band at 605 centimeters minus 1. It's a standard routine measurement, even if you have to make some, you have to put some attention, because there is an overlapping with the two phonon bands of silicon. But probably you don't know that carbon can be detected also by photoluminescence. Carbon in substitutional position does introduce a level in the band gap, but in interstitial position it introduces a level in the band gap. So can be detected by photoluminescence, because usually because it's possible to have the formation of some defect complexes like carbon substitutional and carbon interstitial, or carbon interstitial with oxygen interstitial position. Normally, these defects have been studied in radiation damaged silicon, in which you have an increase in a strong intensity, increase in concentration of interstitial carbon and interstitial silicon, but can be detected also in a solar gray silicon, because you can see, for instance, in this sample that was not a solar gray silicon, was a multicrystalline silicon with a very high concentration. Now was a monocrystalline silicon with a very high concentration of oxygen and also carbon. And we have seen that after a thermal treatment at 450 degrees C for a long time, we detected the C line, the H line, and the P line, so each line that are related to the formation of carbon and oxygen complexes, and also the broad band that you can see has been associated to silicon carbide and silicon oxide nanoprecipitates that can induce strain and are responsible of this broad band, and we will see later. By this technique, by detection C line, it's possible to have a quantification of the low carbon concentration in your sample. Because you know that in the case of Schockley-Queisser silicon and silicon for photovoltaic, the concentration of carbon is always under the detection limit on infrared spectroscopy, but sometimes it's very important to have a quantification of this concentration. concentration, because carbon is in your material and can form complexes after some thermal treatment or process. And so by photoluminescence has been developed a new method that has been calibrated in order to have a correlation between the C line and the carbon concentration. The drawbacks of this method is that the sample must be irradiated with 2 megawatt electrons, and so it's not a simple process, but in any case you can have a detection limit up to 10 to 12 atom over cubic centimeter. And there's been found a correlation between the relative of this intensity and the concentration of carbon. So let's move to oxygen. Oxygen, it's a very well-known impurities. The routine measurement is with infrared spectroscopy at room temperature by detecting a band at 1,166 centimeters -1. But if you have a low concentration of carbon, you can perform measurement of lower temperature, just a liquid nitrogen or lower, and in this case the infrared technique is much more sensitive to low interstitial oxygen, and also it's useful in the case of very thin samples. And in this case you can detect the oxygen up to 10 to 14 because when you go down with temperature there is a splitting of the band position, and also it's possible to see the isotopes of oxygen, so there is a splitting of this band, and by the band position has been calculated a calibration by each band position has been calculated a calibration factor that can be used easily to quantify the oxygen in your material. You can find a lot of information in this very old review paper that was written by a colleague of mine. Now Professor Borghesi has been retired some years ago, but Dele Sassella is a friend of mine and is working with me in my department of material science, and did this very useful review many years ago. Sometimes it's very important to have some techniques that is able to detect the early stage of oxygen precipitation, because I remind you that the silicon is always a solid solution of silicon and oxygen, both in Schockley-Queisser but also in multicrystalline silicon. So it's always a supersaturated solid solution. That means that for any thermal treatment you can induce the precipitation in the formation of nano or micro or large precipitates. So sometimes it's useful to know if you have in your material some oxygen precipitation. This work has been done many years ago for microelectronics application. You know that in silicon the oxygen precipitation gathering is one of the most known process in order to improve the lifetime and the performance of silicon for microelectronics application, but can be useful also sometime to know for photovoltaic application. Thermal donors that are the small oxygen, the nano-oxygen precipitates that are usually formed after thermal treatment around 450 degrees C, but you can have in your ingot, because it can be formed also during the cooling process of your ingot, can be detected by infrared spectroscopy, like dopants that we have seen, because you can see this is the standard range. You can see the lines in the region between 600 and 1000 centimeters -1, and so you can detect the presence, and eventually you can quantify also the concentration of donors, or make a comparison with the concentration of donors calculated by resistivity measurement. Also, by photoluminescence, it's possible to have some information about oxygen. No luminescence lines are associated to oxygen interstitial position, because fortunately the oxygen interstitial position does introduce a level in the band gap, but you can detect thermal donors by the bound exciton lines, like we have seen for any other type of donors and acceptor in your material. By photoluminescence, you can detect at a low temperature, but also sometimes at higher temperature, a band that it's called a P band, that is close to the band of dislocation. We will see at 0.767. Between thermal donors, so we have a big family of thermal donors, but by one of these is called NL8, to a deep center that has been identified by the LTS. So if you have this line, it means that you have a deep center that can affect the lifetime of your material. And so this is the P line. The P line is curious that sometimes is also present at room temperature, so you can detect the P line at room temperature. And in some peculiar work of some years ago, these Japanese guys use this, they use the presence of this visible room temperature line as a diagnostic line to follow the ingot thermal history of the ingot. And so based on the intensity of this line, they decided, they found that the effect of thermal history of their crystal pool was equivalent to an annealing at 500 degrees C for 3 hours. So for this reason, if you're considering that 500 it's a quite dangerous temperature for the formation of thermal donors, it's most probably that in any Schockley ingot that you can that you use also for PV application, you can have some thermal donors inside. It's possible also to have some infer about early stage of oxygen precipitation by photoluminescence, because when much before the thermal donors formation, because when you have just the initial process of precipitation, there is an emission of self-interstitial, because the molar volume of silicon dioxide is larger than the molar volume of silicon. So when you precipitate the silicon dioxide, you have an emission of self-interstitial, and this self-interstitial can aggregate to form the very well-known 311 defect, and this defect is responsible of a line at 0.903 eV that has been also associated to some defect in this work that we have done in collaboration with MIBSOLAR. We have made a correlation between this line and a defect that can be detected by electron paramagnetic resonance techniques. So when you have, so we have seen the early stage, the thermal donors, and then you can have quite a large oxygen precipitation after several thermal annealing process, like is not the standard in the case of silicon for photovoltaic. But if you have a large precipitates, you can detect this precipitate also by infrared measurement at low temperature, but sometimes also I will show you also room temperature. And according to the shape of this band, you can make a correlation between the shape of this band, the position of this band, and also the type of oxygen precipitates, and also the stoichiometry of oxygen precipitates, as reported here. And this can be very useful, and for instance, we have seen many years ago studying in a frame of European project the possibility of using metallurgy grade silicon for PV application. We have seen that in some of these samples there was a so high concentration of oxygens that we have seen at room temperature the oxygen precipitates and the band here indicated in the circle. And in the same sample, by photoluminescence, we have seen a lot of defects. So we have seen all the bands related to carbon and oxygen, the P line, and also we have identified by the shape of the oxygen precipitates band the type of band that we have. So, and then we make a correlation also with transmission electron microscopy that are much more time consuming and different measurements to be performed. But when you have oxygen precipitation, we can have a quite difficult situation in your samples, because you know that when you have oxygen, we have precipitates, you have emission of interstitial, and you can form dislocation in your samples. And you know, by in this team image photo, you can see that there is the class, the nuclei, the oxygen precipitates, and you can see the semi-loop of dislocation that is emerging from these precipitates. So you have both precipitates and dislocation. And also, when you have a dislocation in your sample, the segregation on the precipitation of oxygen along the dislocation is much more probable than outside the dislocation. But we know that when we have a dislocation in our sample, we have the very well-known D1, D2, D3, and D4 bands that can be identified by photoluminescence. So if you have both oxygen precipitates and dislocation, it's not so trivial to understand if which band is related to oxygen precipitates or is related to dislocation. This is work that we have done for many years in collaboration with the Japanese group, because Professor Tajima was the first to assign a luminescence line only to oxygen precipitates and not to dislocation, and to distinguish between a luminescence line related to oxygen precipitates and to dislocation. And this work was carried out also by us in a series of different papers. We did a very long investigation on different type of Schockley-Queisser silicon samples. It treated for different type, for different at different temperature, in order to have more or less all type of oxygen precipitates, nanoprecipitates, oxygen precipitate and dislocation. And also we have done a big work also on plastically deformed silicon in order to make a correlation between the type of dislocation and the D1, D2, D3 bands. And now we can say that you can distinguish between dislocation and oxygen precipitates just by looking at lower temperature about the position of the bands. So we can distinguish between dislocation, silicon dioxide large precipitates, and also nuclei and early stage of oxygen precipitation, early stage of nuclei. This has been proved, for instance, also studying the combination with another impurities that you can have in your samples. Nitrogen. Nitrogen is much more common in silicon for microelectronics, because it was introduced in order to increase the mechanical stability of the Schockley-Queisser silicon. And you can see that if you perform plastic deformation in nitrogen doped Schockley-Queisser silicon, you have the line, the D1, D2, D3, D4 line, and then if you, in nitrogen free, and you perform the same plastical deformation in a nitrogen doped, you can see that we have a completely different shape around D1, because it means that due to the fact that nitrogen increases the segregation of oxygen dislocation, we have a changing in the D-band position, and the emission light is related only to oxygen precipitate, and the D1 is not anymore visible. D1 is still present at room temperature, so I know that you detected many signals related to the D1, but what you detected is related to dislocation mainly, but maybe can be related also to some oxygen precipitates in your sample, or dislocated with oxygen precipitates, can be detected in a multicrystalline silicon, and sometimes if you make a photoluminescence analysis before any solar process, you don't see any D bands. But for instance, in this work in 2005, we have seen that just after the junction formation, you can see a quite high D1 band, and that changing, and it's much more visible due to the segregation of oxygen during this junction formation annealing step. Recently, we have studied the similar problem in standard N-type cell in collaboration with ACN, the Netherlands, on wafer coming from different ingot and different ingot position. They have seen that in some ingot, doesn't matter the type of ingot, there was some wafers and cell that showed some very lower efficiencies, less than 1%. And so we decided to understand which type of defect was responsible of this decrease of efficiencies. Performing photoluminescence mapping and microphotoconductivity mapping, we have seen the famous striation related to the agglomeration of point defect, but we have seen also that there was no correlation between the type of ingot or impurities in the ingot and the presence of striation. But what we have observed is that in the low oxygen content ingot, there were no any evidence about striation. So we thought about the presence of oxygen precipitates on these cells, and so we cut several pieces of wafers in a region with and without striation to perform local microphotoluminescence on these samples. And what we have seen that was, first of all, a strange behavior of the band-to-band emission and also the free exciton emissions, because as you can see here, the intensity was the same at room temperature and low temperature, and this is not the common situation. Normally at low temperature you have a very high intensity of the free excitons, much higher than of the band-to-band transition. And we have seen also there was a strange behavior of the intensity of this band versus temperatures, but we have seen that at the same time there was on striations a broad band around 0.87 that has the opposite behavior of the band-to-band peak versus temperature. And this band was exactly the same that we have detected in Schockley-Queisser silicon sample heat treated at 650 degrees C, so are related to oxygen precipitates. By a comparison between the intensity and the position of this band, we assume that in this sample we have silicon oxide nanoprecipitates with a density around 10 to 11 that can be responsible of striations. This work has been going on with here in the University of WU with Ziv and with Robin. And Robert, sorry, Micro Rob. And so he did a very good job in understanding the level involved in this emission, and also there are some novelty about the level in both in dark and in bright striation that will be reported in his thesis. Recently, we study also by photoluminescence in collaboration with l'École Polytechnique of Paris and the CNRS and the Total Center. They formed a very nice research center in the photovoltaic in Ile-de-France, close to Paris. And they studied a new methodology to form a junction. Is a boron emitter plus P is a boron emitter epi layer grown by lower temperature plasma enhanced chemical vapor deposition. The advantage, of course, is a lower thermal budget, and also it's possible to have a very tuned control of doping profile. But you have to treat the samples after, because you have to activate the boron, or it means you have to deactivate the boron and hydrogen complexes, because you can see by second ion mass spectroscopy you have in this material a lot of hydrogen, boron, oxygen, and carbon coming from the precursors of boron in plasma enhanced chemical vapor deposition. And they have seen some not very good lifetime in this material after this process. And so we decided to study with them the presence of any defect by photoluminescence and also by infrared spectroscopy. We have seen a lot of silicon hydrogen relate vibrational modes due to the high concentration of hydrogen. So you can use infrared instead of SIMS in order to detect the hydrogen concentration. But we have seen this broad band that is not related to oxygen precipitates, it's not related to dislocation, but in this case is related to a standard defect that are formed due to the high concentration of hydrogen. This has been the work that has been done many years ago. When you have a very high concentration of hydrogen, you have precipitation of hydrogen, and you can form the so-called platelet-like defect that can be seen also by TEM measurement. We have some evidence about that, but as we didn't publish yet, I cannot show the transmission electron microscopy, but we have seen that there is a good correlation between this band and the presence of this extended defect. Now I will just very briefly describe a completely different approach of studying oxygen and carbon and in silicon that was for me was very nice and very interesting. I had the opportunity to work in performing experiment under microgravity, and the idea is how we can go further in the control of oxygen and carbon process, and how we can make a new defect engineering of these impurities that cannot be avoided in silicon, is by studying the formation and the segregation of these impurities, because you know that these are related to the melt conventions that govern the formation and distribution of impurities during the ingot growth process. But if perform experiment under microgravity condition, you can have just this process can be studied only under pure diffuse transport condition, and so it's a completely different perspective of view. So, in the frame of an European project that was partially supported by European Space Agency in collaboration with Fraunhofer of Stuttgart and also with Freiburg, the Institute of Growth Material, we try to understand in some ad hoc growth process and also in a microgravity condition process to understand the incorporation of oxygen and carbon and of silicon carbide in solid in ingot. Silicon carbide was studied by the German group because in the case of multicrystalline silicon, probably you know that the formation of silicon carbide particles is very deleterious for a PV application, because they are formed during the solidification process and so are incorporated and can move along the ingot and can create a shunt to the solar cell if you make a solar cell on a wafer in which you have silicon carbide particles. So the idea was to study the movement of silicon carbide particles that is not clear by microgravity experiment. So they performed a ad hoc growth process, is a sort of a float zone growth process in which silicon carbide particles are incorporated on this ingot. Then there was the float zone solidification process, and then this is made in a silicon rod that is completely covered by oxide skin. So sky skin will be the source of oxygen as well, but was created in order to have an abolition of the free melt surface, and so in this case you have a suppression of convention, of Marangoni convention motions, and you have a pure diffuse transport mechanism. So it's a sort of ad hoc, is a sort of microgravity condition growth process. We have studied the distribution of oxygen and carbon in this ingot that we received, and what we have seen is that in this ingot we have an extreme high concentration of oxygen in solution. It means that in the case of this strange or quite close to microgravity condition growth approach, we have a very high concentration of oxygen. It means that the solubility of oxygen in this material is much higher, and you have just the decrease at the end of the ingot. Of course, you can see the ingot, the dimension of the ingot is the order of centimeters. And here we detected, as usual, the nano silicon dioxide precipitates. So we have just a small precipitation of oxygen, even if you have 50 ppm of oxygen in this ingot. So it seems that in the microgravity condition, the silicon oxygen solid solution is much stable, and you have a higher solubility. Then we checked also what happens when you have a silicon carbide inside, and we confirmed that the co-presence of oxygen and carbon can enhance the oxygen precipitation, the co-precipitation. It's very whole work that is based on the fact that we have a combination of an injection of interstitial and vacancies, and by photoluminescence, as expected in this sample, we detected all the line related to carbon-related defects. So the E line, the G line, and also the P line, because we have a nano-precipitate thermal donors of silicon. Then finally we succeed in have a real microgravity Schockley-Queisser float zone ingot grown in microgravity condition with 10 minus 4 G. And so there was launched from a European rocket launch site in Sweden, and then we have about a 6 minimum condition of microgravity. So this is the reason why the ingot is very short. And at the end, we checked the movement of silicon carbide on this ingot grown in microgravity, and they found the German group found a different movement and completely different movement in comparison with a DOC experiment on the ground, and was completely different, was as expected according to theory. As far as concerned photoluminescence, we have seen the signal related to the dopants, and we have seen that there is a uniform distribution of the dopants. It seems that the segregation coefficients of boron and dopant is different in microgravity condition than in the normal condition. And also we have seen that we have just small, no silicon dioxide precipitates, even if also in this case we have a very high concentration of oxygen in our sample. Of course, the theoretical interpretation of this data is not very easy, and also is not so straightforward to make a correlation and application of this information on our work in the frame of silicon for PV application. But I think that it's an interesting and new perspective of studying oxygen and carbon. So I hope to have shown many information that I hope you can be useful for detection of oxygen and carbon and dopants related impurities in silicon for PV. Of course, there are some critical points by this technique because it's difficult to have a quantitative information. Usually you have to perform photoluminescence at a low temperature and also on small samples. So I think that the feasibility of PL mapping on PV silicon can be increased by a combination of PL mapping also with micro PL at a low temperature. And so we have a lot of data information literature. We have to check it carefully. Not always the application on PV silicon is straightforward, but I think that there is still room for research activity despite the number of years and work has been already done. Thank you.